Hello and welcome to Adults Musings. Today we are going to talk about Project Euler and in particular the first Project Euler problem. So let's get right into it. So it's asking about multiples of 3 and 5. So it says if we list all the natural numbers below 10 that are multiples of 3 or 5, we get 3, 5, 6, and 9. The sum of these multiples is 23. Then it asks, what is the sum of the multiples of 3 or 5 below 1,000? So you will see I already have the answer right there. I have already answered this question. But how could you go about getting the answer? So clearly Project Euler has a heavy computer science orientation, but it also has a math orientation. So and certain problems tilt more one way or the other. Personally, I prefer the mathematical problems to the more programming oriented problems. This one has a nice balance. So clearly there's a way to program this, which is the first thing we are going to do. The second thing we are going to do is look at a way to answer this question without any coding at all, just purely mathematically. So let's start off with the coding. Now, you'll notice I'm programming in Java. I already have my class and my main method ready to go. So I will start coding. I will have, that will be my sum variable. So that will store the integer. If for those of you unfamiliar, this int just means it's an integer. So it's a whole number. And it's a variable, so it can be increased or decreased. Then I will have a for loop. I'm going to start with 10 to make sure that we get 23 like we are supposed to. And there we go. That is all you need. So all this for loop does, for those of you unfamiliar, is it has this variable I, which is an integer. So it starts with an integer I that it is equal to 1. It continues. This loop is the condition. So here, every time it goes through, it says, is I less than 10? So eventually, here I am incrementing I. So eventually, I is going to be bigger than 10, because this tells I to get bigger by 1 every time. So the first time I goes through, it checks this if statement with I equal to 1. Then it's going to come through again with I equal to 2. It's going to keep increasing. Eventually, I is going to be 10. And then it sees I less than 10. It says, oh, I is equal to 10. So stop entering the loop. And then it will continue to this print statement. Right here, I am checking if I is divisible by 3 or if I is divisible by 5. That's really what these two statements are. So it says, okay, is I divisible by 3 or is I divisible by 5? If either of those or both of those is true, then increase the total by I. So that will capture all multiples of 3 or 5. And then at the end, here, it just prints out whatever this total is. So if I run this, you'll notice we get 23. like we were supposed to. So now we're feeling pretty confident. So let's have I go up to 1,000. If we run this, we get 233,168, the right answer. Now, before I enter the mathematical part of this video, I want to briefly discuss a different way that you could have written this code. And the different way that you could have written it is as follows. Instead of having if I is divisible by 3 or if I is divisible by 5, we could have if I is divisible by 3, do this, and we could have another if statement. So now we are saying, well, if I is divisible by 3, increase the total by I. If I is divisible by 5, increase the total by I. Now, at first, it may seem like this will give you the same answer, but, and in fact, before I go into it being incorrect, let me show you that for 10, it does give 23. So if you see that, you may say, well, it seems like the logic makes sense. It gave me the right answer for the smaller case, but if you go up to 1,000, you'll notice it's bigger than what it should be. And there's a very specific reason. And the reason is 15. 15 is 3 times 5. And the problem is, here, this first if statement checks if it's a multiple of if the number is a multiple of 3. 15 is a multiple of 3, so the total gets increased by 15. However, it then checks, is it a multiple of 5? 15 is also a multiple of 5, so it gets increased by 15 again. And this will happen with every multiple of 15, because each multiple of 15 divides 3 and it divides 5, so it gets added twice. So we are double counting the multiples of 15. Now there's an easy way to fix this. There are a few ways to fix it, but the way that I will include here is we will say, well, if I is divisible by 15, decrease the total by I. The reason we are doing this is, if we have a multiple of 15, it will get counted here and counted here. So we counted it twice. Therefore, here we'll remove it once. So counted it twice, removed it once, we've only counted it once, which is how many times we wanted to count it. So now if we run this code, you will notice so we get 23, good start, for 10, but what we care about is 1,000. And we get the right answer. So the reason we got the right answer was because we checked, okay, add up all the multiples of 3, add up all the multiples of 5, but when we have a multiple of 15, we have double counted it, so remove it once. Now we are going to apply that very same logic in the mathematical analysis. So if we come down here, notice that there is a way to represent this process mathematically. We are adding up all the multiples of 3 and 5 below 1,000. So really what we're doing is the following. That. However, remember that 15 and all multiples of 15 are going to be in both of these sequences. So we have to subtract one copy, because we're counting one copy of multiples of 15 here, one copy of the multiples of 15. Here, we have 2 copies. So we need to subtract 1 copy. Now that sum, well, those 3 sums added together in this way will give us the answer. What do we do with them? We can do the following. First, begin by factoring out the common factor in each of the sums. So here the common factor is 3. So if we factor out 3, this 3 becomes 1, 6 becomes 2, 9 becomes 3. 999 divided 3 is 333. Do the same thing for this sum. Factor out 5. (995) divided 5 is 199. Do the same thing down here. And 990 divided 15 is 66. So you'll notice now we have these sums are sums of consecutive integers starting at 1. So it's 1 plus 2 plus 3 plus 4 plus on and on and on, plus 331 plus 332 plus 333 in this first case. This was helpful because, as some of you may be familiar with, these are triangular numbers. So triangular numbers are the nth triangular number is the sum of the integers 1 to n. So the fifth triangular number is 1 plus 2 plus 3 plus 4 plus 5, and so on for the rest of the triangular numbers. The reason this is helpful is that there is a formula for triangular numbers. And the formula is the nth triangular number is n times n plus 1 divided by 2. So now we have a way to answer this question. So here, n is 333. So this becomes 3 times 333 times 334 divided by 2. This becomes 5 times 199 times 200 divided by 2. And this becomes 15 times 66 times 67 divided by 2. So now, if we bring in a calculator, we can input 3 times 333 times 334 divide 2 plus 5 times 199 times 200 divide 2 minus 15 times 66 times 67 divide 2. And we get 233,168, the right answer. So this method worked. But this may leave you wondering, why is there a formula for triangular numbers? Why is the formula what it is? And I will quickly show you the algebraic reason. It comes from a certain symmetry that exists in arithmetic series. So an arithmetic series is the sum of an arithmetic sequence. An arithmetic sequence is a sequence of integers where the difference between terms is constant. So, for example, when we had that sum was one of the sums we were interested in, notice that that 6 is 3 plus 3, 9 is 6 plus 3, and so on. each of the you get the next term by adding 3. The symmetry that arises from this is the following. If we just look at, say, 1 plus 2 plus 3 plus 4 plus 5 plus 6, notice that we can pair off terms. So 1 plus 6 is 7, 2 plus 5 is 7, and 3 plus 4 is 7. And this is just a result of the structure that's intrinsic to an arithmetic sequence. So you can imagine, instead of adding up these numbers, we could just say, well, we have 6 terms, which means we can make 3 pairs. So 6 divided by 2 is the number of pairs we have, and each pair is 7. So we can have 6 divided 2 times 7, which gives us, well, 6 divided 2 is 3 times 7 is 21. And that's the right answer. And we can do this in general. Now, I will make a distinction briefly between sums with odd or even numbers of terms. And the reason is the following. So if we had, instead of 6, we went up to 5, you'll notice here we have 2 pairs, and then we have a term by itself. So what do? Well, now we can say, well, now we have 5 minus 1 over 2 pairs that we can make, right? Because here, with these 4, we can make 2 pairs, and then we have 1 extra. Or if I cover up the middle term, would be a better way to show it. If I cover up the middle term, we have 4 numbers, which makes 2 pairs. So we have this. Now their value is, well, 5 plus 1 is 6, 2 plus 4 is 6. So their value is 5 plus 1. And then we have to add on this middle term. Well, this 3 is this term plus 1 divided by 2. Right? Which is a weird way to write 3, but the reason I'm writing it like that will become clear when we look at the general case. So here, this is 4 divided by 2 is 2. This is 6, so we have 2 times 6. Plus, here we have 3, which gives 15, which is the right answer. But notice that instead of writing it like this, we could have factored out, well, let's move this divided by 2 term over here, which may seem strange, but multiplication is commutative, so we can have the 1/2 here, or we can have, or I'm sorry, I guess it would be better to say associative. Yes, that's probably more correct. Because I'm not really changing order, I'm changing grouping. So I'm grouping the 1/2 over here instead of over here. But either way, it remains the same. So now we have this common factor of 5 plus 1 over 2. So if we factor out 5 plus 1 over 2, then we have 5 minus 1 plus 1. These ones cancel, and we just have 5 times 5 plus 1 over 2. Now let's look at the general case. So the general case, if we have an even number of terms, is a bit easier. So if we have an even number of terms, we have n terms, and n is even, then the number of pairs that we can make is n over 2. The value of each of these pairs is n plus 1. and we're done. There's the formula. So we have n over 2 pairs. The value of the pairs is n plus 1. What if n is odd? If n is odd, then we have a middle term. And that middle term will be equal to n plus 1 divided by 2. So we have then n minus 1 pairs. Or, I'm sorry, n minus 1 divided by 2 pairs. We have n minus 1 terms that can be paired off. So n minus 1 over 2 times their value is n plus 1. And then we have this final n plus 1 over 2 term that was in the middle. Well, let's do the same trick we did earlier. We're going to move this 1/2 here, factor out n plus 1 over 2. We have n minus 1 plus 1. Those cancel, and we're left with n plus 1 times n over 2. So the formula remains the same, even if we have irrelevant of even or odd number of terms. So that's why triangular numbers have the formula they have. That will be the end of the video. I hope you all enjoyed it. Have a wonderful day.